I hope you can see the slides.
Yes, sir.
Yeah. So welcome to class 25 of Sage 576. So just to recap what you did in the last class. Okay. So we had started with this relation between the random force and the viscous force. And this relation is called fluctuation dissipation relation or fluctuation dissipation theorem. And this is very important because this ensures equilibrium in the long time. Okay. So that ensures equilibrium in the long time. Okay, and then we did quite lengthy math, and then we had derived this expression where the friction is, which is related to dissipation, is related to this integral of this uh, force correlation at two different time, random force correlation, and this is the mathematical form of your fluctuation dissipation theorem. Okay, so this actually talks about the balance between dissipation and fluctuation, the energy transferred to the system, your cradle particle from the solvent, and the particle dissipates some energy to the solvent. So there's a balance between these two. Okay, and this is another version of the same fluctuation dissipation theorem. And then, like diffusion in position space, we had talked about diffusion in the velocity space, and there we had calculated this delta and delta square average. Delta is not zero in this case, delta average. Delta square average is given by this, and then eventually we have calculated, we have derived what is known as the Fokker-Planck equation, which is like diffusion with the drift term in the velocity space. I think this is where we had stopped in the last class. So uh, we will start from here today. So okay. So today we're going to talk about what is known as Brownian motion uh, in the phase space. Okay. So basically under a force field. Okay. So I can think of this is okay. So let us start with this notation that Q stands for position of the particle to begin with, and P is the momentum of the particle. Okay. So, for example, if I talk about say position at some later time, say I'm calling it, say, what to want to call it, Q1. It is nothing but the position at some previous time Q plus P, momentum, uh, divided by mass, which will give you velocity, times the time difference, the tau. Okay. Similarly, you can think of the momentum, which is given by P plus something like kappa. I'll tell you what is that, into tau. Now this kappa is, from here you can see, this is nothing but force. This is my notation. And if you have a force, momentum is changing because you have a force acting on the particle, and the force, this force is coming from not the random force. Here this force is coming from a potential. So actually it's the derivative of a potential. So this force is a conservative force, which is a derivative of potential. Of potential energy. Okay, so this is a derivative of potential energy. Now, like what we did in other two cases, we write down this distribution function with momentum p plus kappa tau, comma, position q plus p by m into tau, comma, t plus tau. And you know the rule that this is given by integral of the same function with, see, with a momentum, because it is jumping in the momentum space. So p minus delta position q t. Okay, this is again the jump probability, which is p minus delta position q t, and you integrate over all the possibilities of delta. Okay. So now if I expand LHS, you know, standard Taylor kind of expansion, it will give you f of p comma q comma t plus, we take a derivative of this f with respect to p times kappa tau plus derivative of this f with respect to q times p by m into tau, and higher order terms, which I'm not writing. Okay. And similarly, the right hand side also you can write it as follows, which we have done several times. So we'll do Fourier expansion, the Taylor expansion of this, which will give you f p comma q comma t minus delta del f del p plus delta square by 2 del 2f del p square dot dot dot. Okay, and then also you have this this one you can expand. I will take only the first term. Sorry, this is not a function of time, it's a function of delta. Okay. This we have done similar things in the last class. So I'm just continuing writing the right hand side. Right hand side is now actually, you can take this f p q to outside, and then you'll have integral of this jump probability function phi, which is phi times pq delta. Okay, and then you'll have something like the first derivative with respect to p. Just go back, you can see this term with respect to t, and then you had f, and then you had this integral. You will have this integral delta phi pq delta. Then the next term is obviously second derivative with respect to and as you can guess, the first term here, the integral here is 1. It's normalized. So what you have here, you end up with So I can just write down the whole thing here. The left hand side was, if you remember, it was f plus this. So let us write down f also. F pqt plus first derivative of f with respect to say p. We had this into k tau plus first derivative of h respect to q with this. And on the right hand side, you have, I'm not writing this again, okay, these things. So now what I can do, of course, this f and this f on from both the sides, you can cancel this and this will cancel, okay. And then uh, del f del p, I just divide by tau both sides, becomes plus, okay, I had not put one thing actually, I should have done this, I forgot. What is that? Yeah, there's another term which will talk about explicit time variance, isn't it? This one into tau. So I'll have one more term here, del f del tau. Anyway, so we have del f del q by m plus del f del t into tau. Sorry, the tau have divided with. So this one is going to be equal to this, and on the left hand side, right hand side rather, I'll have I hope all of you are following. So this is very similar to what we did in the last class.
On the RHS, why do we have a jump only in momentum space?
Because here the jump is in the momentum space because your position, because we are not looking at, like, you have a diffusion of course, but uh, what happened that here, how do I say, uh, it is diffusing, the particle is diffusing, but the uh, mm, but the jump, let me explain this better. So because you can have a, when you have position and momentum, in this case we just look at the diffusion in the position space, although the particle's position is changing in the phase space, because the particle diffusion is happening in the, what is happening, that you have an external potential. Because of this external potential, there is a force acting on this particle, and because of this force, the particle position and momentum is changing. You can definitely integrate over the position jump, but if we don't do that, okay, now maybe I'll come back with a better answer why it is, I don't know. Okay, I'll come back with a better answer, because I think maybe in the next class I'll be able to answer your question better, why we don't consider, because next class we'll talk about overdamped dynamics. Once you know overdamped dynamics, then you will see the difference between overdamped and underdamped. Here is an underdamped dynamics. So because of that, we are considering jump only in the momentum space. Okay, Anish.
Okay.
This underdamped means it is not highly viscous limit. Here the inertia is important. So I preferred, so it is, so momentum comes first, then position. Okay. There's a concept called of, see, the slow variable and fast variables. Here the fast variables are anything other than position and momentum. So position and momentum are the what do you call, are the slow variables. Yes, the slow variables. In the overdamped case, your slow variable is uh, your moment, your position. So when in the next class, probably next or next to next class, the last, I don't know how many classes I have, uh, we'll talk about briefly at least this overdamped dynamics, and there I'll explain when it is the jump in the momentum and when it is jump in the position. So we'll take it for granted. Let us see how it comes out. Okay, it will be better if I explain after I discuss overdamped dynamics. Yeah.
Okay, sure.
Yes, yes. So this one, of course, you know what is this? We had a name, like it's very similar. It is nothing but this. This is M1, I think, no? M1 PQ, I can call it. And this one is like M2 PQ. We had done it earlier. And let me write down the equation. And if you, of course, it is like that. And you know what is K? K is not K, is kappa, rather, it's dV dq, which is minus V prime Q. So if it is minus V prime Q, and also you know that this is equal to minus gamma V, this is gamma kBt by m. And I do a change in variable, say I take mass equal to 1, I call position as x. If mass becomes 1, then P is V. So if I do all this and I take this two term on the other side, what I'm going to get like del F del T, del F del T. Of course, this F is a function of x comma V comma T. This is equal to this is equal to, if I take this on the other side, see, you have this and this. So what I'm going to get del F del X, because Q is X, my notation, and P by M is V, del of V. And this one will again become, this is minus V prime, so it will, on the other side, will become plus del F del V V prime X. And then I'll have minus, here I'll have minus del V of gamma V X X V T plus, of course. And this equation has a name, like Fokker-Planck equation. This is called Kramers equation. Okay. Kramers was a famous physicist. So this is called Kramers equation, and it is very important today for today's class and for the class after this. Okay, so we have this Kramers equation. So let me write down the Kramers equation again here. So Kramers equation is x v t. So basically, I'm talking about a Brownian particle in a force field. Equation of motion for that is equal to minus del f del x into v plus del f del v into p prime x minus del v to gamma v. Of course, I'm not writing a comma v comma t again. Anyway, I can write if you want. Okay, it should write here as well. This Kramers equation, and actually You see that if I take only this part, this part is nothing but your what is known as Liouville's equation. This part corresponds to Liouville's equation. Liouville's equation you know already.
Yes, sir.
And you know that if I have Liouville's equation, then if I have a situation that del f del t goes to 0, this will give me equilibrium distribution, isn't it?
Yes.
Or steady state, whatever. One of the steady state distribution is the equilibrium, no? So say let us equilibrium distribution, and you see that if I put this part 0, then this part plus this part becomes equal to 0, and you see that in that case you will have a function which is a function of x and v only, no time dependence, and it will have something like some normalization constant here called 1 over z exponential of minus half v square plus vx divided by kVt. You can check. One can check this. Now this is what you expect, isn't it? This is your Boltzmann distribution. How many of you can see that this is a Boltzmann distribution?
Yes, sir.
Because your system, your Hamiltonian of the system is p square by twice m. P is m times v. M is 1, so it is v square by 2 plus the potential energy v of x. And so essentially it is nothing but 1 over z, isn't it? So this is your Boltzmann distribution. Or actually you should call Maxwell-Boltzmann distribution, because we also have, doesn't matter, your equilibrium distribution. That I'm not checking, you can just check it, because you have to put this part equal to 0. Wanted to check that you take this, take a derivative with respect to x and v, you'll put it there, you'll see that it satisfies this equation. Okay. So this is how it is. Now what I'm going to talk about is very important for chemistry, physical chemistry. This is called Kramers' theory of activated processes. Okay. We're going to deal with this. And this is one activated process is for a chemist is actually chemical reaction. So I can think of a situation like this. I have a double well, asymmetric double well, say. Okay. Of course. And this direction is x, and this is also your reaction coordinate. Very simple model. Of course, this is potential energy. We're dealing everything in the language of potential energy, not free energy. And say this is a position which is called XA. This is a position which is called, say, XC. And there's a barrier, and there's a position for the barrier top, XP. So I can call that XA is the reactant state. Now XC is a product state. What is XB? XB is the barrier top. Okay, very simple. Now, few more things. Say this energy is a VA, and say this energy is VB. Okay, not this energy, sorry. Uh, this is okay, VB, and okay, this position is B, this position is A, this position is C. Okay, and this is VB, VA. So it is obvious that this energy, if I call it E, then what is E? Yes, from here you can see VB minus VA. And this is, you know, this is called activation energy. So I can think of a chemical reaction. It could be, say, for example, a small organic molecule going from one isomer to another isomer, and there's a barrier. Maybe the double bond has to be broken, and then it will rotate, and then there will be formation of double bond. The energy barrier. This could be this X could be the angle around the double bond. That is your reaction coordinate. So VV minus VA gives you the activation energy required. So the particle is here. The particle means your reaction coordinate is here, and the reaction coordinate itself is executing random motion, because if I take a molecule and put in water, it will be bombarded by water molecule. It will execute random motion. So all the coordinates will execute random motion. So there will be friction, of course, coming from the solvent. So I want to calculate what is the steady state rate. Steady state rate from going to reactant state to the product state. Okay, so that is what we want. We want to calculate the okay. So we consider that what are the assumptions? Stationary situation. So that we can calculate a steady state current at the barrier top here. Okay, so basically what I'm saying that, okay, I allow the particle to equilibrate around this reactant well. It equilibrates, and then there will be rare events. One of the particles will get some energy and it will surmount over the barrier. Okay, so these are rare events, of course, but yeah, I am to calculate this in the steady state. Okay, so what does it mean? You want to calculate the steady state? It basically means the equation shown here, this Kramers equation. So let us change our variable. I just change it to, I call it P rather than F. Many books they call it P. Just a change in notation. So if you are looking at the steady state solution, obviously what is the condition?
Del P by delta 0.
So this we should do. Okay. So in the steady state, we want to calculate what is the rate of going from here to Okay, so we'll do that. So steady state means, of course, your equation now becomes, if you look into this, your equation, what are the equation? This equation again I'm writing, okay. Your steady state solution, okay. So at the barrier top, we assume that potential is linearized, okay. So if you're at the barrier top, the potential is now Vx is actually Vxb, and then I can do a Taylor expansion, of course. Okay. Now, as you know that what is this? This is zero at the barrier top, maxima minima. You know that. And barrier top has a curvature which is negative curvature. So I can write this as, say this. So this, the whole quantity, the second derivative of v with respect to x. I can write it as something like omega b square. So basically, I assume there is we just approximate the barrier top with an inverted parabola, inverted harmonic oscillator, okay? Inverted parabola. So it is going to be minus half so inverted parabola. Okay, at the barrier top, inverted parabola. Okay. So, but what happened near the bottom well? What do you expect? I assume we have equilibrium, essentially. So the particles fast equilibrate at the bottom well, and then it will leak. So the barrier has to be quite large. If barrier is small, then even before it attains this Boltzmann distribution, it will leak. Then this description is not valid. So the barrier has to be large. Barrier is large enough so that you have enough time for this particle to settle down and have a Boltzmann distribution in the around the reactant well. So what is the Boltzmann distribution around the reactant well? You can write it down. This will be something like again. Of course, I'm just writing because you know. Of course, I have to calculate this at. Okay, is this fine? And also, we do the same thing at the bottom well. I write down potential as a just Taylor expand, I linearize the potential. So it will be like XA. The first term is going to be 0, but let me write it down. And the second term is this is again 0. So you have Vx half, should have half Is this fine with all of you?
Yes, sir.
Yes, sir.
Okay. So now first we calculate, or we'll just write it down at least formally. What is another population? In the well A, reactant well. What will be the population? I'm calling it NA. Now population is, you have to integrate over all possible value of X, V, and you have to have this steady state thing. This is your population. Okay? Is this clear?
Yes.
Ideally, this should be minus infinity to the well, but we have taken the upper limit to x infinity. This is another assumption, okay? Because we assume that beyond that well, there are not many particles. So we can integrate all over the space, okay? All over the space. Now, next thing, another thing we need to calculate, this is called the flux. Flux J over the barrier. So this is a steady state flux at the barrier top. Can anyone tell me what should be its formula? Actually,
Rate change of the probability distribution.
it actually nothing but your P times XV, this. This is your at the barrier top. Okay, this is your flux in the barrier top, and the steady state rate is given by okay, it is called flux over population, and that is your rate constant. What is this again? How much population around the reactant well, that you have to calculate in the steady state, and the flux at the barrier top, and divide this flux by population, you'll get the steady state rate. So this will have what will be the unit for this rate? Any idea? Actually, you can calculate. You can just no, you can just come up with the unit. Unit is going to be inverse, time inverse. It's a frequency essentially. You can go and check yourself. Okay. So this is just like a fast order reaction, calculating the rate of first order reaction. Okay. So now we proceed with the calculation of G. And we construct, to begin with the construct, okay, my steady state P comma P of X comma V is something like xi X comma V. This is just a time exponential of look at it very carefully. When xi is equal to your some constant, normalization constant, a proper normalization constant, this gives you Boltzmann distribution. So it's not Boltzmann distribution. So this accounts for deviation from Boltzmann distribution. So that's why it's not equilibrium distribution. It is steady state distribution. Is this clear?
Yes.
Yes.
So I have now what I need to do now. I need to take this and put it in my Kramers equation. I have del P del T equals to 0. So I have the right hand side of the equation. And actually, after a little bit of algebra, one can show which I'm going to write down actually, that because I'm at the barrier top, Now you can guess that why it is so, because you have the exponential factor will cancel, you know, and this one you get because you take a derivative of potential with respect to position. So that's why it is linear, harmonic, so that becomes linear. Okay. Now can anyone tell me what will be the value of this xi when you are in the well A?
1/z.
You are right, kind of right, but the way it is done, so you can call it 1. Okay, I can just call it 1. Okay, or some constant, of course. Like I can always multiply this with some factor and make it 1/z, but it is a constant. Okay, and if I go away and say beyond the barrier top, what will happen? When your x is greater than xb, what do you expect? This, it is 0 actually. This is another assumption, which basically means as the particle reaches the barrier, it will go to the other side, and when it goes to the other side, particle is being removed. There is no particle on the other side. Okay, this is a, so you have only reactant well barrier top, then there is beyond barrier top your xi is 0. Okay, this
Sir,
is how,
what
so as
about
if the particles are removed when it,
sir? What about at position C? Is it is also an equilibrium point? So why not?
position C, I just wrote it, I just drew it, but it is not there in this picture. So as if beyond the barrier there is something like a sink, the particle goes and get absorbed. So the idea is that if the particle breaches the barrier, crosses the barrier, not reaches, if the particle goes crosses the barrier, goes beyond xb, then it is absorbed. So the reaction has taken place like this. Okay, so this is the assumption. So you put a sink there as if it absorbs all the particles. Now particle means my reaction coordinate in this case. Okay, now let us do some few more things. uh, we use the following linear transformation, which is very important, because now it is going to be a little lengthy, but it is important that I do this. Say I take u equals to v plus x minus xb into small a. Okay, a is a constant, to be determined later. Okay, if I have this, obviously I can write that del x equals to a times del u, and del v equals to del u. Okay, now I can use these variables and write down the above equation. If I write down the above equation, I'm going to get something like minus va del u, sorry, minus omega b square x minus xp plus gamma v. Now del v is del u plus gamma kVt, and this one you know that del 2 del u square, the whole thing is operating on psi, which is x comma v. Of course x comma v means also x comma u, you can call it now, to 0. Is this clear to all of you?
Yes, sir.
It is not very difficult. Now I just write it down again. K gamma kVt, I write down the last term first. This is fine, no? I think this is exactly what you have here. This
Yes.
one, yeah, you had. Okay. So after this, we did little bit of algebra again. Okay. So let this quantity omega b square to x minus xp plus phi gamma plus a equals to minus lambda u. Okay, I assume this is minus lambda u. Okay, this is what? Constant. This constant we have to determine later. If this is the constant, then what will happen? Now remember, since u is v plus a into x minus xp, we had it, no? So now I can put it here. This b, that omega b square x minus xp plus v into gamma plus a is equal to minus lambda v minus lambda a x minus xp. This will tell me what? This will give you that minus lambda a equals to omega b square and a plus gamma equals to, tell me, minus lambda. Okay, so which also means that a square plus gamma a equals to minus gamma a, and this means that if I now from here I can write on the other side 0, you will have a square plus gamma a minus omega b square, isn't it? This, you can just get rid of lambda from here and you get this quadratic equation in a just by adding these two. Add this and this. So this is called 1. This is, okay, don't need to do it. But you can see what I have done. A very simple thing actually. Just add this and this. Omega b square minus lambda a equals to a square. So a square plus lambda a minus omega b square is equal to 0. Now you know how to solve this. You know this, that if I have ax square plus bx plus c 0, then what is x? X has two roots and they are minus b plus minus. You know, all of you know. This a and this b are different, of course.
Yes.
Yeah. So this is a side note. So now you just look at it, and then if you do that, then you find x is your a here. A is minus gamma plus minus root over gamma square minus 4 w omega b square. Sorry, by 2. Which basically means minus gamma by 2 plus minus gamma by 2 whole square minus omega b square. Okay, this is fine.
It should be a plus under root, right?
No plus.
No, gamma square plus 4 omega b square.
Yes,
Plus.
yes, sir. Yes, sir.
No, then I'll have a problem here. Then I'll have a problem. Is it plus?
Well, as per the quadratic equation is a square plus gamma a minus omega b square. So minus 4ac is minus 4 into 1 into minus omega b square.
No, I understand, but maybe the notation, I have to check the notation. Yeah, omega b square. This is minus lambda u, I'm calling it. And your u is v plus a into x minus b. And then you have omega b square x minus xb plus v into gamma plus a, which is this, equals to minus lambda v minus lambda a. Okay. So in that case, okay, mm, because yes, it should be plus, no? I guess it is plus. So let us have it have a plus there. Okay, and then I think up to this is fine. Okay. Okay, let it be there. Now I come back to this equation, what the equation I had. I had an equation, it's quite lengthy actually. I had equation like this. Let me write down gamma kVt sorry. Okay, this is the equation we had, no? And then what is this? This is I should write down then gamma kVt is this is lambda u and let the y. Then what I have here, I have something like gamma kVt, sorry, and this one is y prime uh, so you can call it like just okay. So I have gamma kVt del y del u plus is equal to minus lambda u into y, and this means that lambda by gamma kVt and to du. This is fine with all of you? Should be fine, no? There should be u actually, u into du. Okay. So now if I now integrate, I'm going to get ln y equals to minus lambda. This will give u square by 2 twice gamma kVt into u square. Of course, some constant. So I call it ln f2, integration constant, a constant of integration. Okay. So if it is like this, then y is f2 exponential of minus lambda u square by twice gamma kVt. Huh? Then what is your xi u. Xi u, you know that you have to integrate this with respect to u. So you'll get f2 you can call it u prime. I'm just calling it du. Don't mind. So 0 to u. Is this fine?
Yes.
Now we are at the barrier top. That is what we are doing. Okay. So we look for a solution that vanishes as x goes to infinity. Okay, which basically means what? But the above integral should be finite, no?
Yes.
For all mod u. It is a square, it's an exponential, it's a quadratic in u, so it's like a Gaussian function. Now this implies what? Lambda has to be positive. Is this fine?
Yes, sir.
And what was lambda? If you go back, you see the lambda was minus omega b square by a. So it basically means the negative root of a should be taken, no? Should be chosen, isn't it?
Yes, sir.
So that minus divided by minus becomes positive. So lambda is positive. In order to ensure lambda is positive, one has to take negative root of a. Okay? And what was the expression for a? A was, remember, minus gamma by 2 plus minus, so I will take the negative root. Okay, so this is the root you should take. Are you convinced?
Yes, sir.
Now, when your x goes to infinity, large distance, what will happen to u? Can anyone tell me what will happen to u? You look into the linear transformation. U is what?
B plus x minus xb.
No, it is v is u plus x some into something. So u is minus x times something plus v. So it should go to the other direction, isn't it? Go and check. Let us. I don't know where. Okay, it is maybe here. Here.
Yes. So if x goes to infinity, then u also goes to infinity.
Yes. Is it correct? Is it u? Okay. So that I have to check. They have a small problem here. Because if you what was the expression for u? Yeah, it is v. I thought if it is v, then v is minus infinity. No, if it is v, not u. Okay. No, I'm fine because your a is negative, isn't it? We have just find negative root. Anish, that is why it is in a is negative. It's a negative root. So this statement is fine because your u is v plus a into x minus xp. This is negative, so u is also negative of x proportional to the minus x. So which basically means when x goes to infinity, I told you that your this function has to go to 0. The long go away from the reactant well is 0. So there is no particle there. There is no reaction coordinate should be the probability of finding x is 0 rather. So on your left hand side I'll have 0 because what I'm doing this. What are the expression? This one I'm calculating. 0 and then the first term is f1. I just put it like f1 plus f2 0 to minus infinity here because your u goes to minus infinity when you talk about x goes to infinity, and then you have exponential of minus lambda u square by twice gamma kbt integrate. Is this fine with you, Anish? Should be fine.
Yes.
Okay, so it basically means that f1 is equal to f2 with minus infinity to 0. I just change the integration limits. And I can do one more thing. I can write it as I think this is fine with all of you. And you can evaluate this integral, no?
Yes.
Because let me tell you, e to the minus alpha x square this is the answer, no? So here
Yes.
it will be pi by alpha means this is alpha. So it will be twice gamma kbt per half. So again, this 2 you can, it is nothing but f2 pi gamma kbt. This is your f1 in terms of f2. Okay?
Yes.
So therefore I can write xi, function of u of course. It is now f2 times plus, you had this, no?
Sir, you missed a lambda, I guess, in the integration.
Yeah, lambda, no? Yeah, so it should be a lambda in the denominator.
Yes, sir.
It should be here. Yes, you're right. You're right. Very good. Follow. This is how it is, your xi, no? Is this fine with all of you?
Yes.
Should be fine. Now you remember what was p of x comma v? It was xi x comma v times this exponential factor, the exponential minus beta h kind of thing. Remember that?
Yes.
Okay. So basically now I can write into, you have exponential of, go and check your This is at the barrier top we should do. This is how it is, isn't it? P of x comma v. It has to be like this.
Yes.
Then, like at, if I do it explicitly, if I do this at x equal to xb, what I'm going to get? I'm going to get this is f2. Look at it. This is constant. No, vxb is a constant. So I can take this out. This is fine? Is this fine with you? Into, say, what I'm going to get, this one I'm calling it C. So let us call C equals to this whole thing. That's a big thing to write. You write C into exponential of, let's look at it, it will be minus half, sorry, this one. From here, this first part. First
Yes,
part.
sir.
Because exactly at x equal to xb, this part is 0. Okay, so I'll have this, only this part, plus I will have what? I will have I'll write down what it will have. I'll have something like f of x comma v into exponential of. Now you can guess what is f of x comma v. F of x comma v is here, this integral. Of course, like not x comma v, but it is x comma u rather, because integration limit is this. Let's call it, like you can call it x comma v. If okay, actually the problem is that I'm writing everything in v, so this one also will become v, isn't it? Yeah. Same problem, right? But you can understand what I'm trying to say here. Yes. This is exponential of into lambda. You have gamma also. V. Okay. This is how it is, isn't it? P of x comma v. If I write in terms of v.
Yes, sir.
So I think we better I open a new one because it's quite heavy now. I don't know whether I can open. Take a break for a minute or two. Because once you write too many equations, then it becomes quite heavy, and then you cannot okay, just tell you what was j. J is v p at the barrier top, no? Now the first term is 0. I'll have a term like this, which is v. This is 0, no? Because we'll have a
Yes.
term like this here, this one.
Yes.
This will be 0 when you integrate this. So what I'm going to get, if I write j will have like f2 exponential of minus v of xp by kbt integration v e to the power of minus v square by 2 kbt f xp comma v dv. This is what you have. Let's look at it. Because this part is 0, you'll have only this part multiplied with this part and integrated over v after multiplying with v. Okay? Is this clear to all of you?
Yes.
Yeah. So now I can write it as like whatever f2 now this integration what I'm going to do, I'm going to write it like this. I hope you understand because I have done such tricks many times. This is fine, no?
Yes, sir.
This is a trick I did. And now I am going to do integration by parts. You know, integration by parts is like this.
Yes.
You have two functions, f g, then you know that it is f dg is equal to f g minus g df, isn't it? This you know. So what I'm going to get, if you do integration by parts, good. Minus kbt is outside, and if you do integration by parts, so this is your like dg, so your fg becomes and then your integration is exponential of minus v square by this is how it is, isn't it?
Yes, sir.
Yes, sir.
Sorry, and this part is 0 because it is Gaussian function you have multiplied with, isn't it? This plus has to be 0. This is not 0, this is okay. So we're left with this part. This and this minus will combine. So I have to wait because okay. So what I have here is j is equal to f2 exponential of minus b of xb by kbt, and this is kbt. This minus and minus will combine, and you have this is fine, no? This is how it is.
Yes, sir.
Now, since you have xv is this, then it means that if I take del f del v is only the integrand.
Yes.
Okay, not u but v, because the function of this is fine, no, Manish? If I write like this, so now I have to put this here. So if I put it here and do it here, j is whatever this is there, f2 exponential of kbt is there, and then have integral. So I'm just skipping one step. Just I can take this minus v square common. No, I can take. Okay,
Yes.
kbt also common.
Lambda by gamma plus.
Yes. So then you will have you will have one. You had this is here. You'll have lambda. You'll have lambda by gamma, isn't it? And you will have plus 1 into dv. This is what you have, no?
Yes.
And then if you do the integrals, let me do it here. If you do this integral, obviously what are you going to get? You're going to get pi to the power of half divided by this is what you have, no? Isn't it?
Yes.
And you can rearrange it. Let me rearrange and write down the final expression. If you rearrange it, you are going to get something like twice pi kbt. Okay, from here, and then you will have gamma divided by lambda plus gamma whole to the power of half. This is fine, no? This is what you should get. Okay. So this is your
Yes.
expression for J, flux at the barrier top. Then you calculate the population, which is Na, and the definition is this is the definition. Okay. And
Yes, sir.
and what do I do now? So now what I do,
Separate variables.
same thing we do, and doing the same thing, you can actually evaluate this because what you have here is p x comma v. This is what we did, isn't it? And now we are going to do it around the reactant well. Okay, so your v is going to be vxa plus this is what you are going to do. Okay, Now if I take this integral, now if you write down this p of x comma v, which is your f2, you just check your notes. Okay. Of course, if it is v, then you should put v here. It doesn't matter. You can put also u. Let it be u. And then I take this u to be going to infinity, large value of u. Then what will happen to this integral? What will happen to this integral? Tell me.
Half of root by half.
Yeah, this will also give you something like exactly the same thing here. Okay, and then this is going to be f2, this plus this. Yes, so it is going to be
Root over
2
gamma
times here. It's like that.
by lambda. Yeah.
This one, which is
Yes.
twice pi gamma kbt whole to the power of half. This is your p of x comma v.
Lambda.
Yeah, your lambda should also be there. Yes, your lambda should be there, divided by lambda, but is inside the bracket. Okay, so what I yeah
Xi, right?
what
This is the expression for xi of xv. This into exponential beta
yeah
Hamiltonian.
sorry yeah, you're right. So Na is going to be, now you know that you integrate this, so this is constant, so the constants I can write it like this, f2 now this part again will give me exponential of minus vxa by kbt, isn't it? Because I put this one. Okay, and then I have, because I have to integrate around x, not exactly at xa, around xa. So what I have here, I have two integration. One is this, the integration over v. Then I have another integration. This integration is okay. This is what should go, because when I put this here, you will have v squared term, which is this, and then you also have x minus xa whole squared term.
By kbt.
Flux is calculated exactly at the barrier term, but here the population means you have to integrate around the minima xa. Okay. So if
There
you
should
do
be a by kbt, right?
which one?
That is. Yeah.
Yes, obviously, yeah. Okay. So now if you integrate, what I'm going to get? You had this Na, you had this f2 twice pi gamma. You have a class after this. People who has class, they can leave, they can see later. Maybe I'll go 5 minute extra today. This one is there, no? And this integration you can do, this one and this one. The first one will give you twice pi kbt half, and then you will get I hope that I have done everything correct. Yes. Okay. So this is the expression. Okay. This was the Na.
Yes.
And you had the expression for J. So if you write down the expression for J was something like F2 twice pi gamma kBt whole to the power 3 by 2, I think I had, by omega A, because kBt to the power half and then 1 kBt was there. Anyway, and you had like gamma by lambda whole to the power of half. Sorry, not this one. I just, okay. Make something stupid here. First, let me write down Na, the final form of Na. F2, this, twice pi gamma, not gamma, twice pi kBt divided by whatever is there, but this one whole to the power 3 by 2, because this, but this gamma will come out. You have gamma by this lambda whole to the power of half exponential of minus Vxa by kBt. Okay. This is your expression for Na, and you had the expression. Anything is missing? Omega A. Yes. And you had in J, you had this expression for J was like this. One by twice pi. You can go and check. That was the expression for J. So K going from A to C, the steady state rate is the flux over population. And this is going to be gamma by lambda plus gamma whole to the power of half omega A by twice pi. You can see that this is going to happen. This will cancel, isn't it? This will cancel. This and this will cancel. And this gamma and gamma will cancel. That's why you have gamma by I think this is fine. This is gamma or lambda. This is fine, no? Anish?
Yeah, Na is fine.
Na is fine, no? What was J2, F2? So J was this gamma by lambda plus gamma.
Yes, per half.
Yeah, so I have put this gamma by lambda plus gamma per half. Okay, so that is there. Yeah. But what else? Yes.
Into that will get multiplied with lambda by gamma per half. Because
What did I say? What?
You have gamma by lambda per half in the denominator.
Yes.
So that will cancel gamma per half. That will
Yes.
become lambda by lambda plus gamma.
Yes, I just want to, and then, okay, let me write down the exponential factor. The exponential factor is minus Vxp minus Vxa by kVt. This expression is fine if I write down like this. Everything is cancelling. Anish?
Just that gamma by lambda per minus half.
Yes. That should be there. Yeah. So what I'm going to do, I'm going to stop here because I have some amount left. I don't think I can do it today. Okay, we'll do in the next class. From here, we'll see what is going wrong here. Small mistake. So we'll stop today. And thank you very much for your attention. We'll talk. We'll come. The next class is on Monday.